Welcome to the DIY Honda Garage channel. The diagnostic trouble code, DTC P16E5, indicates a LIN communication error specifically related to the PCM and the DC-DC converter in the 2017 to 2022 Honda CR-V. LIN stands for Local Interconnect Network, a communication protocol that allows electronic components within the vehicle to share information. The issue suggests that there may be a disruption in the communication line between the Powertrain Control Module, PCM, and the DC-DC converter. The PCM is responsible for managing various engine and transmission functions, ensuring optimal performance and efficiency. Meanwhile, the DC-DC converter is crucial in converting voltage levels to maintain battery charge and power. This error typically arises from wiring issues, poor connections, or even component failures. To properly address this error, a structured diagnostic approach is required, starting with verifying the issue using diagnostic tools like the HDS, Honda Diagnostic System. The P16E5 code specifically points to a LIN communication failure between two crucial components of the Honda CR-V, the Powertrain Control Module, PCM, and the DC-DC converter. The PCM operates as the vehicle's central brain, controlling essential functions such as fuel injection, ignition timing, and emission controls. The DC-DC converter plays a pivotal role by converting high-voltage direct current from the hybrid battery to low-voltage direct current to power other vehicle systems. Both components are typically housed in the engine compartment, meaning any wiring issues or connections can easily stem from this area. Identifying the specific points of failure is vital for accurate troubleshooting, especially since issues like loose terminals or damaged wires can lead to miscommunication and performance degradation. When diagnosing the DTC P16E5, several potential causes can be discerned. First, loose or corroded connections are common culprits, as they can disrupt the LIN communication protocol. This often occurs at connectors or terminals that may be exposed to elements leading to oxidation. Secondly, damage to the wiring harness could cause short circuits or breaks in communication lines that inhibit data transfer between the PCM and DC-DC converter. Additionally, a failed DC-DC converter itself can also trigger this error if the unit can't properly relay functional information. Lastly, a malfunctioning PCM may send or receive incorrect data, ultimately leading to an interruption in the communication chain. Understanding these factors is essential before moving into more in-depth testing. Symptoms associated with the DTC P16E5 can include several observable issues. Most notably, the illumination of warning lights on the dashboard, particularly those indicating hybrid system malfunctions or battery-related alerts, can provide a primary indication of trouble. Additionally, drivers may notice reduced engine performance, as the PCM might not be able to optimally manage functions due to communication errors. This can translate to rough idling, acceleration hesitations, or other drivability concerns. Battery charging issues are also a common symptom. The LIN communication loss may prevent the DC-DC converter from receiving proper operational commands, leading to insufficient power being provided to recharge the 12-volt battery or to supply necessary voltage for other electrical systems. Recognizing these symptoms is vital for initiating the troubleshooting process. The first step in troubleshooting DTC P16E5 involves verifying the problem. Begin by turning the vehicle to the on mode, allowing the vehicle's electronics to power up. After that, use the Honda Diagnostic System, HDS, to clear the DTC, which effectively resets the fault memory. Once the DTC is cleared, switch the vehicle to off mode to power down all systems completely. Following this, turn the vehicle back to the on mode and wait approximately 10 seconds to allow the systems to restart correctly. Finally, check for any pending or confirmed DTCs once more using the HDS. This process will help identify whether the code reappears, confirming an ongoing issue with the LIN communication between the PCM and the DC-DC converter. During the second troubleshooting step, any existing pending or confirmed DTCs should be reviewed again using the HDS. Specifically, check for DTC P16E5, which indicates a LIN communication error involving the PCM-DC-DC system. If this DTC is indicated, you will move on to Step 5. If DTC P16E5 does not present itself, you will progress to Step 3. This analysis is critical as it helps to narrow down the specific areas of concern, allowing for a more focused troubleshooting approach. Maintaining an accurate record of any other DTCs can also serve as useful data in understanding the broader context and history of the vehicle's issues. In this third step, the focus is also on revisiting the list of pending or confirmed DTCs using the HDS. Specifically, you will be looking for DTC P16E5, which indicates a LIN communication error related to the battery sensor in the PCM-DC system. If this code is flagged, move on to Step 9. If not, you will advance to the next step. This repeated checking for codes is crucial because it helps to find the relationship between various components and errors that may affect the vehicle's functionality. Identifying multiple issues can be especially important since they may point to a common problem area requiring intervention. Continuing troubleshooting with Step 4 involves another review of pending DTCs using the HDS. This time, you are checking for DTC P16E5, which points to a LIN communication error specifically involving the shutter grille. If this DTC is present, proceed to Step 13. If not, advance directly to Step 17. This step highlights the interconnected nature of electronic systems in modern vehicles. Various issues may emerge that can appear to be isolated, but are fundamentally related to the same communication failures between various ECUs, electronic control units. Therefore, each step in this process builds on the previous findings. In Step 5, you will begin to pinpoint the failure area related to the LIN communication. Start by turning the vehicle to the off or lock mode, ensuring that all electronic systems power down. Next, disconnect the DC-DC converter connector A3P. Once the connector is removed, it's essential to measure the resistance between two specific test points. Test point 1 is the female terminal number 1 on the DC-DC converter connector, and test point 2 is the body ground. The measurement should be taken under the test condition of having the vehicle in the off mode with the connector disconnected. If the resistance is measured at 1 megaohm or more, then you will advance to Step 7. If it is not, you will proceed to Step 6. In the sixth troubleshooting step, the focus shifts to verifying any possible shorted wires within the LIN communication line. Start by jumping the SCS line using the HDS and patiently wait for more than 1 minute to allow the system to stabilize. Direct your attention to checking for continuity by measuring between the DC-DC converter connector A3P, terminal number 1, and the body ground. This should be conducted while sequentially disconnecting a series of connectors: the alternator 1P connector, the PCM connector A50P, the 12-volt battery sensor 2P connector, and both the upper and lower shutter grille connectors. If, during this process, you find that continuity goes away upon disconnecting any of these, the LIN wire is deemed intact, and you should replace the part that caused the disconnection. However, if continuity remains, you will then need to repair any short circuits found in the LIN wire. The seventh troubleshooting step involves re-establishing connections after preliminary checks. Start by reconnecting the DC-DC converter connector A, 3P, to ensure proper functionality. After reconnecting, the next step is to disconnect the alternator 1P connector. This step is essential as it isolates the alternator from the electrical circuit's integrity so that it can be tested without any influence. Measure the resistance between the first female terminal in the alternator connector and the body ground. This must be measured while the vehicle is in the off or lock mode. A resistance reading of 1 megaohm or more indicates integrity in the circuit, allowing you to proceed to step 8. If the resistance is less, the DC-DC converter will need to be replaced, as it might not be functioning correctly. In step 8, the approach involves conducting open wire checks in the LIN communication line. Again, start by jumping the SCS line with HDS, waiting for more than 1 minute to ensure stability in the system. After that, disconnect the PCM connector A, 50P, and the DC-DC converter connector A, 3P, setting up for the resistance measurement. Now, measure the resistance between two newly defined test points. The DC-DC converter connector A, 3P, female terminal number 1 and terminal number 10 in the PCM connector A, 50P. This measurement should occur under test conditions, where both connectors mentioned are disconnected and the vehicle is off. If the resistance reads at 1.0 ohm or less, it confirms that the LIN communication wire is good. In this case, verify any authorized service information or consider substituting a known good PCM. However, if the resistance is higher, repairs should be made to the LIN wire between the PCM and the DC-DC converter. The ninth troubleshooting step entails determining the possible failure area involving the LIN BAT sensor line. Start by ensuring the vehicle is in the off or lock mode. Once confirmed, disconnect the DC-DC converter connector A, 3P. It is crucial to isolate this component to assess communication integrity accurately. Measure the resistance between test point 1, which is the DC-DC connector A, female terminals number 1, and test point 2, which is the body ground. This measurement should occur with the vehicle completely shut off and the connector disconnected. If you find the resistance equals or exceeds 1 megaohm, it indicates a good wire integrity, leading you onward to step 11. However, if the resistance is lower than 1 megaohm, you will proceed to step 10 for further analysis. In this 10th step, it focuses again on checking for shorted wires related to the LIN communication. Start by jumping the SCS line once more with the HDS and allow for a minute to pass. The objective is to check for continuity between terminal number 1 of the DC-DC converter connector A, 3P, and the body ground while systematically disconnecting various connectors: alternator 1P, PCM connector A, 50P, battery sensor 2P, and both shutter grille connectors. As you disconnect each connector, monitor if continuity disappears. If it does disappear with any one of these connections, it indicates that the LIN wire is fine. You should then replace any disconnected component that caused the continuity loss. However, if no discontinuity is found after disconnecting all, be prepared to repair a short in the LIN wire that connects the DC-DC converter, alternator, PCM, shutter grille, and battery sensor. In 11th troubleshooting step, the primary goal is to further diagnose the potential issue area surrounding the DC-DC converter and related wiring. Begin by reconnecting the DC-DC converter connector A, 3P, to allow effective communication during testing. Next, disconnect the 12-volt battery sensor 2P connector. With these connections manipulated, measure the resistance between specific test points. The second terminal of the 12-volt battery sensor and body ground. Ensure that this measurement is taken while the vehicle is in the off mode and the connectors stated are disengaged. If the reading measures at least 1 megaohm or more, it indicates the circuit is likely undamaged, allowing you to move on to step 12. If it's lower, then the DC-DC converter will need replacing. Step 12 focuses on continuing the open wire check within the LIN BAT sensor line. Again, jump the SCS line with HDS, allowing a minute for the system to stabilize. Afterward, disconnect both the PCM connector A, 50P, and the DC-DC converter connector A, 3P. Once these are disconnected, measure the resistance between the DC-DC connector A, 3P, terminal number 1, and PCM connector A, 50P, terminal number 10. This requires that both connectors are disengaged while the vehicle remains in the off state. If the resistance is indicated as 1.0 ohms or less, the LIN communication wire is confirmed as functional, allowing you to check for any authorized service information related to the codes or symptoms you are troubleshooting. Alternatively, if the resistance reading is higher, repair an open in the LIN wire that connects the PCM to the DC-DC converter. Step 13 aims to identify the potential failure area within the LIN BAT sensor line. Begin by turning your vehicle to the off mode to ensure all systems are inactive. Similar to previous steps, disconnect the DC-DC converter connector A, 3P, which allows you to isolate its effect on the wiring. Measure the resistance between test point 1, the female terminal number 1 on the DC-DC converter connector A, and test point 2, which connects to body ground. If the measured resistance is 1 megaohm or greater, continue on to step 15. Should the resistance fall below this threshold, proceed to step 14 for further investigation into possible shorting or wiring issues. In the 14th troubleshooting step, you will conduct a check for shorted wires in the LIN communication lines. After again jumping the SCS line using HDS and allowing it to stabilize for more than a minute, systematically disconnect the same connectors as before to assess continuity. This includes the alternator 1P, PCM connector A, 50P, 12-volt battery sensor 2P connectors, and both shutter grille connectors. The objective here is to determine if continuity drops off as you disconnect any of these components, confirming the health of the LIN wire. If you experience a loss of continuity with any connector disconnection, it indicates that wire integrity is intact. Proceed to replace any faulty components that caused the disconnection. If continuity remains constant, then focus on repairing any shorts in the wires connecting the DC-DC converter, alternator, PCM, and other components. In this 15th step, the troubleshooting focuses on possible issues around the DC-DC converter while checking connections relevant to the shutter grille. Begin by reconnecting the DC-DC converter connector A, 3P. Next, disconnect both the upper and lower shutter grille connectors, 4P. This allows you to isolate the shutter grille components during testing. Measure resistance between the number 3 terminals on the shutter grille connectors and body ground, ensuring the vehicle remains in off mode during this process. If your reading shows a resistance of 1 megaohm or higher, proceed to step 16. A lower resistance reading indicates there could be a fault in the DC-DC converter needing replacement. The 16th troubleshooting step revisits the open wire check in the LIN communication system, targeting the LIN BAT sensor wiring line. Once again, start by jumping the SCS line using the HDS and allow adequate time for stabilization. Disconnect both the PCM connector A, 50P, and the DC-DC converter connector A, 3P, before proceeding to the resistance measurement. It is crucial to take the reading between the DC-DC connector A, 3P terminal number, 1 in the PCM connector A, 50P terminal number 10, performed while both connectors remain disconnected and the vehicle is off. If the resistance is 1.0 ohms or less, it verifies that the LIN communication line is functioning correctly, permitting a review of authorized service information or substituting a known good PCM. Conversely, if the resistance exceeds this level, pay close attention to repairing the LIN wire between the PCM and the DC-DC converter, as it signals an open circuit. In the 17th troubleshooting step, focus shifts to verifying fuse integrity. Start by ensuring the vehicle remains in the off or lock mode. Next, check the status of fuse D21, which is critical for the LIN communication system's power supply between the DC-DC converter and other components. If the fuse is operational, you will advance to step 18. If the fuse is blown, it signifies a potential short in the IG1 ACG wire, which connects the DC-DC converter to the fuse. In this scenario, not only must you replace the blown D21 fuse, but you also need to address the underlying wiring issue that caused the fuse to blow in the first place by repairing the short in the line. The final step in the troubleshooting process entails checking for an open wire in the IG1 ACG line. Ensure you disconnect the DC-DC converter connector A, 3P once more to isolate the circuit. Next, with the vehicle switched to the on mode, measure the voltage between two defined test points, terminal number 3 of the DC-DC connector A and body ground. Ideally, you should see battery voltage reading at this stage, which confirms that power is flowing through the IG1 ACG line properly. If you find that battery voltage is absent, it suggests an open circuit in the IG1 ACG wire that connects the DC-DC converter to fuse D21. Thus, further investigation and repair of this wire connection will be necessary. After completing all necessary repairs and maintaining connectivity of the LIN wiring system, it is imperative to confirm the success of these repairs before concluding the process. Begin by clearing all DTCs using the Honda Diagnostic System, HDS. This action resets the fault codes stored within the system, allowing you to verify whether the issues have been resolved. Following that, it is crucial to conduct a thorough test drive of the Honda CR-V under various operating conditions to validate that no warning lights reappear and that performance has returned to normal. This step provides an additional level of confidence that any underlying issues have been completely addressed. To prevent future occurrences of DTC P16E5, implementing a consistent preventive maintenance routine is essential. Start with regular inspections of the wiring and connectors associated with the PCM and DC-DC converter. Ensure there are no signs of wear, corrosion, or damage that might lead to communication failures. Keeping connections clean and secure protects against dirt or moisture, which can degrade performance. Additionally, timely replacement of fuses is crucial, as blown fuses can indicate existing wiring issues that should be repaired proactively. Considering these preventive measures will help maintain the integrity of the electrical systems, reducing the likelihood of future DTCs and ensuring consistent vehicle performance. In conclusion, the DTC P16E5 denotes a LIN communication error between the Powertrain Control Module and the DC-DC converter in the Honda CR-V from 2017 to 2022. Identifying and diagnosing this issue involves understanding the interconnected nature of the vehicle's electronic systems, utilizing a systematic troubleshooting approach guided by specific steps. Importance lies in accurate measurement and testing of both wiring integrity and electronic components to pinpoint failures. Effective repair and preventive measures, such as maintaining clean and secure connections, are crucial in preventing future issues. Following these guidelines promotes long-term vehicle reliability and performance, ensuring that the driver experiences a smooth and trouble-free journey. Please like and subscribe to the channel. See you next time.